Okay. With class being aborted on Monday, I actually did not have a whole lot lined up to cover on that day. So what I'm going to attempt to do, I'll certainly cover that today, and I'm going to see what I could do in what was the lesson originally planned for today. That's lesson 23. We'll see how it goes. I may not get to everything, and if not, then I will deal with that on Monday. Okay. Now, the first part of it is dealing with the. I wish I could make this text bigger. I'm not sure why it's not cooperating. I'll have to deal with that later. But what are you going to see here in the wave equation? We've seen the Cauchy problem, where you're solving it on the entire real number line, minus infinity to infinity. And also semi-infinite domain, where you have a boundary condition at x equals 0, and then you're solving for x going off to plus infinity. So now we're going to have boundaries, have two boundaries, left and right boundaries. So we're dealing with a finite interval. So that's the subject of this lesson, lesson 20, a finite vibrating string. So this will be kind of problem that you're familiar with from separation of variables for the heat equation, only now it's going to be the wave equation. So a problem we're going to consider is this. So here's our wave equation on the interval 0 to L. And then we have our initial data, and since it's UTT in the PDE, we need U of x0 is f of x, and UDT of x0 is g of x. So our two initial conditions. And then we're going to assume homogeneous Dirichlet boundary conditions, and I'll talk about Neumann boundary conditions later. But as an example, we'll just stick with this. So we can proceed the same way as we did with a heat equation. We can solve this problem by separation of variables. So I'll go through that process. So you might find this a helpful review of separation of variables. It's all the same until we get to the part of the ODE that depends on time, because that will be different from a heat equation. So like before in separation of variables, we assume our solution is a product of a function of x and a function of t. And then because the PDE is homogeneous, the boundary conditions are homogeneous, and the PDE is linear, if we have several functions of this form, we can add them all up, and it'll still be a solution of the PDE. And it'll still satisfy the boundary conditions. So we substitute this form into the PDE, and this is what we get. Taking second derivative with respect to t here, with respect to x here. And then some rearranging. And we get this expression that depends only on t, this that depends only on x. Therefore, both must be equal to a constant, k. And from that, we get these ODEs that have a very similar appearance. Both are second order ODEs this time, just with different coefficients. And then ODE in x has to satisfy these boundary conditions that come from the original problem. Okay. Now, we have to consider cases of whether the constant k, which is called a separation constant, is positive, negative, or 0. And if we let k equal to 0, so then x double prime is 0, then x of x has to be a linear function of x. Well, the only linear function of x that's equal to 0 at these 2 points is line capital X of x is 0 everywhere. So we need non-trivial solutions. So k equals 0 is ruled out in this case. If k is positive, what would happen in that case is we solve for this ODE for capital T. The general solution of this ODE would be for positive k would be combination of a growing exponential and a decaying exponential. And that exponential term that would grow over time is a non-physical solution. And because you're not going to have a vibrating string that is going to have displacement growing over time without bound. It's just not physically possible. So we rule out the case of positive k also. So negative k is all that's left. So we write k is equal to minus lambda squared, because that will definitely be negative. So now these are ODEs with this filled in for k. So then, now this is the same kind of ODE we dealt with in X for the heat equation. But now, notice, because the ODEs have pretty much the same form, the only difference is we have a c squared in the one for t. So the general solutions are almost exactly the same. It's just that here you have cosine of lambda x, here we have cosine of c delta t and sine of c delta t. So now for boundary conditions, we set x equals 0 and x equal L in here. So like before, lambda L has to be an integer multiple of pi. So now we have these solutions. So we have sine n pi x over L for n being a positive integer. So these are our eigenfunctions of this problem. And the eigenvalues are n pi over L squared. And so far, we've seen no difference from the heat equation except for this. Now we fill in those values of lambda for Tn of t, and this is what we get here. So now we have these constants, Cn and Dn, that have to be determined from the initial data. Just like with the heat equation, we had one constant for each n that came from the one initial condition that problem had. Okay, so this is what our general solution looks like that satisfies the PDE and given boundary conditions. So now how do we take care of the initial condition? Well, if I plug in t equals 0 in here, the sign will go away. This whole term goes away. The cosine will be 1. So I just get this. And it has to equal f of x. Similarly, if I take the derivative of all this with respect to t, then from this term, I'm going to get cosine Cn pi t over L times Cn pi over L. So this constant factor will show up in the time derivative. I again plug in t equals 0. This term will go away because taking a derivative of a cosine will give me a minus sign. This is a term that sticks around. So now this is what I get for the time derivative at t equals 0, and that has to equal g of x. So notice it's almost the same. It's just that because here we took a derivative with respect to t, we have this extra scaling factor that's Cn pi over L. Okay. So another way of looking at it is Cn is a Fourier sine series coefficient of f. And in this expression, Cn pi dn over L, that is a Fourier sine series coefficient of g. So we can find a Fourier sine series of f and g, and that leads us to our constants Cn and Dn. So if I incorporate that into my general solution up here. So here we have, this is a formula for Fourier sine series coefficients on the interval 0 to L. And then I do the same thing with G, except I have to divide by Cn pi over L. In other words, I'm multiplying by L over Cn pi. So I get an L in the numerator that cancels with the L in the denominator that comes from the formula for Fourier sine series coefficients. So this is what I get for dn. So when you're solving this kind of problem, wave equation, finite interval Dirichlet boundary conditions, you can actually jump directly to this. Because for those boundary conditions, the same ones that I showed here, the solution will always be of this form. The only thing left for you to do is get the coefficients Cn and Dn from your initial data. And that's for these boundary conditions. I can't emphasize that enough. The solution will have a different form if a boundary conditions change, and I will show you an example of that right now. But first, does anyone have any questions up to this point? Okay. All right, let's see, we have more people up here. That's good. But also one person gone. Hopefully they come back. Okay. Now let's change the boundary conditions and see what effect that has. So now we have Neumann boundary conditions. So du dx is equal to 0 at x equals 0 and x equals L. Then if you were to go through that whole process again, what you would find is that these are the eigenfunctions. They would be cosines. So remember, if we have boundary conditions on u at both ends, that's sine. If it's du dx at both ends, that's cosine. If it's a mix, like for example, excuse me, suppose u is 0 on the left boundary, and then we have du dx is 0 on the right boundary. That still is going to be a sine, but a different sign. You recall that came up in one of the homework problems. If it's the other way around, du dx is 0 on the left, u is 0 on the right, that's still going to be a cosine, but a different cosine from this. Very important point. When it's these boundary conditions, k equals 0 is permitted because you can have a constant function that would satisfy both boundary conditions. So that's why when you write your eigenfunctions, xn of x, here n starts at 0 rather than 1, because if I plug in n equals 0, I'm going to get 1, and a constant function is a viable solution to the PDE with these boundary conditions. Same eigenvalues as before. Same general solution, except you also start with n equals 0. So when n equals 0, you're just going to have a constant because sine of 0 is 0, and then this cosine becomes 1. So then your solution formula is like this. So very similar to the other. Here we have a cosine instead of a sine. And then here we have C0 over 2. The over 2 is notational convenience. Here are the formulas for Cn and Dn. Very similar to before. Again, n starts at 0 for the C's. And the reason why we divide by 2 in this case, we don't absolutely have to, but that way we have one formula for all of the C's. That covers C0 and the other Cn. Whereas if I did not have this 1/2 factor here, I'd have a special case. C0 would be 1 over L times this integral. And then for dn, we have this. This is just like same dn as before, only a cosine instead of a sine. Also going from n equal 1 to and so on. Because dn is multiplying a sine, we do not need a d0. Okay. So that's how you handle a wave equation on a finite, a bounded interval with different boundary conditions using separation of variables. All right. So really, these are formulas that you like use on a homework problem or a test to solve these kind of problems. So you inspect the boundary conditions, see, okay, that tells you which situation you're in, and can use these formulas from there. Like, so this for the Neumann case, and the other for the Dirichlet case. Now, that completes everything from lesson 20. As you can see, it didn't take very long. So now I'm going to transition to lesson 23, which is on a very different sort. It actually revisits something that we saw at the very beginning of the semester. Classification of PDEs that are general linear second order PDEs. So I'm going to review what you saw back then. If you had a general second order linear PDE of this form, whatever coefficients a through f and whatever function g, that you could classify it as a hyperbolic, parabolic, or elliptic. For now, we're most interested in the hyperbolic case, since that is what the wave equation is. Now, but we didn't really do anything with the classification back then, but it's actually quite useful for developing solutions of PDEs, because once you've determined what type it is, that gives you some guidance on how to transform the PDE into a simpler one. We saw we did that with a wave equation. We use a change of variable we use a change of variable to obtain a much simpler PDE, solve that one, and then the elaborate solution formula arose from that. But I have to admit that change of variable that I showed you to develop that formula, and when I presented that topic, it was really pulled out of thin air. There wasn't any real justification for using a change of variable. And that's what I'm going to provide here. Where does a change of variable like that actually come from? Yeah. All right. And classification of PDEs is a first step towards doing that. So the idea is for general second order linear PDE like this one. So we are going to make a change of variable, but at this point, I don't know what a change of variable is. But I want to change from my current independent variables x and y to these independent variables, c, also known as squiggly, and eta, so that the PDE is a simpler form. Like maybe it's something that I can solve just by integration. So what I need to do is express all these partial derivatives from the original PDE in terms of these new variables. So that means a whole lot of chain rule. So for instance, for du dx, that'd be u squiggly x plus u eta x. The idea is that x and y both depend on c and eta together. Now, if I do the same thing for uy. And then I can apply this chain rule again to figure out the second partial derivatives. So if I take the derivative of this whole expression with respect to x, that would be the same thing as taking a derivative of this with respect to xc and multiplying by xcx, and then taking a derivative of it with respect to eta and multiplying that by eta x. So, but the thing I have to keep in mind is, if I take a derivative, okay, I'm not sure where the individual terms come from. Like when I work on this one, I have u xc, and then I multiply this by xx, and that gives me xx squared. But then, I get the same thing over here, u eta, and then I have eta x squared. But I also have to differentiate this with respect to xc. So I get u eta xc. And similarly from this term, I get u xc eta. So at least of these two cross terms here. But when I'm differentiating with respect to x, these are differentiated with respect to x also, and that's what leads to xcxx over here. So really what's happening is, when I take a derivative with respect to x, I'm going to have the product rule. So 1/2 of a product rule that's applied to uxc and u eta gives me all of these terms. The other half of a product rule applied to xcx and eta x here give me these two terms. Okay. Okay, I have okay. So this is what the product rule gives, but and you can see the last two terms come directly from here. To work out the rest of it is where I'm using this formula again, because here I have derivative of u with respect to xc and then with respect to x, but I can swap these. I can take derivatives in whatever order. We're assuming appropriate continuity of certain partial derivatives to do that. So I can write this as ux with respect to xc. Similarly here, I can write this as ux with respect to eta. And then I have my formula for ux up here that I can substitute. Oh, I'm sorry. I made those edits in the wrong line. So now my steps are a little out of order. So just for the sake of the notes, Okay. I take this formula for ux and substitute it in here. And that's a way to get to the rest of the terms. Okay. Okay. Now, I could do the same for the mixed partial derivative, uxy, and then uyy, using the same chain rule ideas. Okay. So now I have all the derivatives from the original general second order PDE rewritten as partial derivatives with respect to only xc or eta. So now what I can do is I can substitute all of these formulas for these partial derivatives into that PDE, and then I can group them by which derivatives with respect to xc or eta. So, for example, I can gather all the u xc terms together, or all the u eta terms together, and that tells me what the new coefficients of a PDE will be. So now, in new variables, this is my PDE, where these coefficients come from the original coefficients as follows. So we see that, for instance, the new A bar, comes from A, B, and C, the original PDE, and it involves partial derivatives of C with respect to X or Y. And similarly, the coefficient for new C involves partial derivatives of eta with respect to X and Y. Okay. So now, what we like to do is choose xc and eta so that these new coefficients are simpler. Now, at this point, I've not assumed anything about the PDE being elliptic, hyperbolic, or parabolic, but now I will. I'm interested in the hyperbolic case. So the idea is I want to transform the PDE to this one where the coefficients A bar and C bar are 0. So now I only have this among my second derivative terms. And then I have these other terms involving only a first order derivative of u or just u by itself. Because, for example, if the PDE u xc eta equals 0, I know how to solve that. We did solve it to get D'Alembert's solution formula. So how can we choose xc and eta to force these coefficients, A bar and C bar, to be 0? So if I set A bar and C bar equal to 0, then I get these equations. So what I did was, for example, I took this one, set it equal to 0, but I divided both sides by xcy squared. So that's why I have xcx over cy, the whole thing squared, and xcx over cy. But here I just have c by itself. The reason why I did that for both a bar and c bar, so that came from here, is now I have a quadratic equation in these ratios, so I can solve for them. in terms of the original coefficients A, B, and C. And what's important here is, since the coefficients are of a quadratic are A, B, and C, and the PDEs is assumed to be hyperbolic, I know that b squared minus 4ac is strictly positive. That means I will have two distinct solutions. That's very important. So I'm going to use set xx over cy to be equal to one of the roots of this quadratic equation, a to x over a to y to be equal to the other root. So that's what I get here by choosing a plus sign here and a minus sign here. So now, what I have is, like, because this will come from my coefficients. This will be something that's given. I have to just work it out. And since it's equal to xc over xcy, I basically have first order ODEs for xc and eta. So what I'm going to do is I want to express xc and eta. I want to define them in terms of x and y by setting c equal an arbitrary constant, eta equal to arbitrary constant. So basically, I'm plotting like coordinate curves in the xc eta plane. So if xc is a constant, then dxc, so d for derivative, would be 0. But by chain rule, I would have this. So this must be 0, and it's similar for eta, which is also assumed to be constant. So now what I can do is I can rearrange both of these, and now I have dy dx is equal to minus this root, and also dy dx is equal to minus this root. So now I have these ODEs that I can try to solve using whatever you learned in your first ODE class. Now, once you solve them, and I will show an example a little later, the new coefficient b bar that you're looking for, the only non-zero one of these first three, here's the original formula for it. So then you can substitute your formulas for xc and eta throughout here by taking your derivatives with respect to x and y. And here I've done some factoring to be able to express b bar in terms of these ratios that we saw earlier, because these came from the quadratic formula. And here, this is one root, here's the other root. So here we have a product of the roots. Here I have a sum of the roots, and that's very helpful because one nice thing to know about quadratics is anytime you have a general quadratic equation, the sum of the roots is equal to minus b over a, always. The product of the roots is always equal to c over a. So instead of working with these, I can just substitute c over a here for a product and minus b over a for the sum. And then I can just simplify this as much as I can. And it works out very nicely. What do you get? You get the discriminant, which you already know is positive. And then times this scaling factor here. So this is your formula for the new coefficient, for the coefficient b bar in your new PDE. So once you figure out xc and eta, you can just jump directly to this. And you already know that a bar and c bar are 0. That was by design. So now you have this new PDE of this form, where you have this principal part. That's the only term that involves a second partial derivative, and then these lower order terms. So depending on what d bar, e bar, and f bar are, you can hopefully find this easier to solve than the original. Because a lot of a theory about second-order linear PDEs just makes the assumption that the PDE is already in canonical form. Now, what I've shown you here only works for hyperbolic PDEs, because in that case you get two distinct roots of your quadratic equation, whereas with parabolic you only have one distinct root, and then with elliptic you don't have any real roots. Okay, actually that's... Okay. All right. So now I'm going to step through an example involving a hyperbolic PDE. All right, so here's our original PDE. So we have our A, B, and C. And then our change of variable to exceed eta satisfies these equations. So from our quadratic formula, if we fill in A, B, and C, this is what we get: x over y in this case, and then minus x over y for this case. So then we have these ODEs to solve. So really jump to this ODE for dy dx is minus x over y, and then dy dx is x over y. Now these ODEs are separable. So what we get is y dy is minus x dx, and y dy is x dx. So now you can integrate both sides of these like you would for any separable equation. And this is what you get. So here I have y squared plus x squared is equal to a constant. So xc is basically the constant of integration that comes from integrating both sides of this. And then here we have eta is equal to y squared minus x squared. So now we have formulas for xc and eta. So what's the new PDE? Well, just the coefficients. So a bar is 0, that's by design. B bar, we substitute, take derivatives of xc and eta with respect to x or y, and substitute all of those in here. And this is our coefficient, so minus 16x squared y squared. C bar is 0 by design. And then your remaining coefficients. Now, what's interesting is in the original PDE, you only had A, B, and C. You did not, D and E were both 0, but you do get non-zero D and E, unfortunately, from making this transformation. So here's D and here's E. Formulas for these were shown earlier. And then when you're making this kind of transformation, the terms F and G don't change at all. So if they were 0 before, they're 0 now. So the transform PDE, but in the original variables, because that's what I filled in here for like D bar and E bar, looks like this. But what you like to do is write this PDE entirely in terms of xc and eta. You want x and y out. So what helps is if we go up here, y squared plus x squared, that's xc, and y squared minus x squared is eta. So we can fill those in here and here. But it takes a little more algebra to handle this. But what you end up with is this coefficient. So this is b bar in terms of xc and eta. So this is your PDE that's entirely in new variables. So questions about this example. Now, one of the homework problems from this lesson. Okay, lesson 23. Okay. So I assigned problems 3, 4, and 5. 3 and 4 are basically stepping through this same kind of example for a given hyperbolic PDE. You confirm it's hyperbolic, and then you go through this whole process to find your transformed PDE. Then problem 5, it's marked on the site as a bonus problem, so you don't have to do it. That deals with what's called an alternative canonical form. So I'll take a moment to show you that. So another canonical form for a hyperbolic equation is after you get into this form, you change variables again to xc plus eta and xc minus eta. And that gives you do the same ritual for partial derivatives. And so to express uxc, u eta, and uxc eta using a chain rule. And then what do you end up with when you substitute these into your transform PDE? Is your coefficient b bar is now a coefficient of second partial derivatives with respect to alpha twice and then beta twice. And then you have these other lower order coefficients. So the nice thing is that this is reminiscent of a wave equation with a coefficient of 1 basically, because the coefficients of these are the same. So problem 5 deals with taking the PDE from problems 3 and 4 and carrying this out to get this alternative canonical form. Okay. Whenever I look at the participant list, a different person is left. All right. But yeah, I mentioned there's a lot of technical difficulties today, just like I had. Okay. So now we're caught up, in spite of not having Monday, and we still have some time. Does anyone have questions like on any ongoing homework problems?
Lesson 17.1.
I know I have some. If I check my Canvas dashboard. Oh, yeah, I have a whole bunch of homework 5s to grade. That's something that I will deal with this weekend. So I guess you all are between homeworks now, pretty much, or most of you anyway. I see that 9 people have turned that in, so we're still a few outstanding.
Can we go over 17.1?
Okay. If there really are no questions, well, anyone can stick around if they do want to ask something, but I will stop the recording here.